Exercise 2.2. Prove that a simplified rational function of the form r of x equals ax squared plus bx plus c divided by dx plus e can never intersect with its oblique asymptote. Here a, b, c, d, and e are arbitrary real numbers, so I'm gonna divide the top and the bottom by d and just rewrite r of x as ax squared plus bx plus c divided by x plus d, where again a, b, c, and d are real numbers, arbitrary real numbers. So this just makes the calculations slightly easier. And, well, you can use polynomial division to find the oblique asymptote first of all. So ax squared plus bx plus c, and then we would need to multiply this by ax. So we get ax squared plus adx, and then we do our subtraction and we get b minus adx plus c, and then we would need to multiply by b minus ad. And then, just to finish it off, d times b minus ad, and so the remainder term is going to be c minus d times b minus ad. But that's not really important. What is important is this part here, which is our oblique asymptote, because it means that ax squared plus bx plus c divided by x plus d is equal to ax plus b minus ad plus this thing, c minus d times b minus ad divided by x plus d. So this is our function r of x, and as x tends to infinity, this part tends towards 0. So that means that r of x tends towards ax plus b minus ad. Okay, so now we want to prove that now that we've found the oblique asymptote, we want to prove that our rational function r of x can never intersect with it. So r of x is equal to ax squared plus bx plus c divided by x plus d, and if it were to intersect for some value of x, we would have that this is equal to ax plus b minus ad. And then from here it just becomes about algebra. Let's multiply both sides by x plus d. So we get ax squared plus bx plus c is equal to ax times x plus d. So that would be ax squared plus dax, and then it would be plus b minus ad times x, and then plus b minus ad times d. And then we can cancel the ax squareds from both sides, and then there's also a dax minus adx, so we can cancel that. So we're left with bx plus c. Well, I guess we can also cancel the bx's. So we just have c on this side, and then on the other side we have bd minus ad squared. Or, if we want to write it in a more familiar way, we can say if and only if c minus d times b minus ad equals 0. And if we scroll up to our previous calculation, it's basically telling us it can intersect if and only if the remainder is 0 when we actually do the polynomial division of ax squared plus bx plus c divided by x plus d. In other words, if r of x can intersect with its asymptote here, if there is some value of x to make this equation true, it has to be the case that the remainder in this polynomial division equals 0. In other words, x plus d is a factor of r of x, and in fact we would have that r of x is equal to its asymptote, so it's equal to ax plus b minus ad if this is true. And I guess you can notice that this doesn't depend on x here, so if we have the remainder in the polynomial division being 0, then it's true for all values of x, because in that case the rational function would be equal to its oblique asymptote. And that proves that a simplified rational function can never intersect with its oblique asymptote, because if we do have that x plus d is a factor of r of x, then it is not a simplified rational function. And so it's done.